Okay, today we're going to be talking about number 8 on the angular momentum WebAssign. The main themes incorporated in this problem are Newton's laws and rotation. The setup is that there's a pulley and there's a string wrapped around it. Attached to the other end of the string is a block. The block in this problem weighs 11 grams or 0.011 kilograms, and the radius of the pulley is 1.85 centimeters or 0.0185 meters. We're going to be solving for three things: the angular acceleration, the tension in the cord, and the moment of inertia of the pulley. It's important to know that the block is released from rest and falls down. And we're going to be solving for all three of these things as the block falls down. It gives us one thing, and that is that the acceleration of the block as it falls is 1.335 meters a second squared. The very first thing that we're going to be solving for is angular acceleration. We know that when it comes to pulleys, angular acceleration is equal to your translational acceleration over the radius of the pulley. So if we plug in these numbers, we get alpha is equal to 1.335 over 0.0185. This ends up being around 72.16 radians a second squared. For the second part, we're going to be solving for the tension in the string. To do this, we're going to be using Newton's second law, which states that force is equal to mass times acceleration. As you all have done before, to do this, all we need to do is create an FBD for the block, and the only two forces acting on the block as it goes down are tension in the negative direction and gravity in the positive direction. It's positive because that's the way that the block is moving. Okay, now if we want to write this out, it would be mg minus t is equal to mass times acceleration. Positive force, negative force, mass acceleration. If we plug in our numbers, we get 0.011 times 9.81 is equal to 0.011 times acceleration. Simplify, we'll divide 0.011, 9.81 by 0.011, and we forgot to subtract t, so here's t, is equal to, and we have our acceleration up here, 1.335 meters a second squared. Once we type all this into our calculator, we find that t is equal to 0.0932 newtons. Now that we have both the tension in the string and the angular acceleration of the pulley, we can find the moment of inertia of the pulley. To do this, we're going to be using two equations that we have previously learned. Those are torque is equal to inertia times angular acceleration, and torque is equal to force times radius. In our case, the only force acting on the pulley is the tension in the cord. So this is equal to torque is equal to tension times radius. We're going to be using these two equations and plug in our own numbers, which are that 0.0932, the tension, times 0.0185, our radius, is equal to our inertia times our angular acceleration, which is 72.16. Once we plug this into the calculator, we find that our moment of inertia for our pulley is 2.389 times 10 to the negative 5 kilograms meters. For this last part, I'm going to be showing you the real-life setup for this problem and what you actually just solved for. I tried to set this experiment up as close as I could to the problem you just solved. The radius of the pulley is the exact same as before, and we once again acted like the string that the block is attached to has negligible mass. The weight of the block plus the flashcard is also 11 grams, just like before. The flashcard is there so that the position sensor, which you can see on the floor, can read the block's change in position accurately. Once I started recording the position of the block on my computer, I released the pulley and let the block freefall. Obviously, the position sensor is collecting data throughout this whole process. The data that you see on the screen now is the position data of the block during the freefall. The highlighted portion of the data contains the only relevant information because this was the time interval from the very beginning of the block's fall to right before the block came in contact with the position sensor. It was with this data that I calculated the acceleration of the block over this interval, which we then used to calculate the angular acceleration of the pulley, the tension in the string, and the moment of inertia for the pulley.